let us begin again. We end up in discussing, we were discussing corrosion protection by electrochemical methods, and we have also seen that there are two sections. One is cathodic protection, another one is anodic protection. We started cathodic protection, and we saw that where we can go for cathodic protection, and some of the places we cannot go for cathodic protection. For example, we have seen that the locations where the structure is above water line or above the surface of the earth, that cannot be protected, because since there is no electrolyte. Now, another place where if we have a shielding effect, that case we cannot go for cathodic protection. Another case where we have non-conducting solution, for example, oil which is non-conducting oil, we cannot go for cathodic protection. Now, another place where if the system is highly corrosive, okay, if the electrolyte is highly corrosive, then we should not go for cathodic protection. So, in order to have cathodic protection there, we need to spend a lot of current, we need to spend a lot of money. Now, we saw those two cases. Now, let us start with the principles of cathodic protection. Principle of cathodic protection. Now, while we discuss principle of cathodic protection, we will take help of mixed potential theory again. Now, we have seen that if the structure, this is the metal object which is to be protected cathodically, we have an auxiliary electrode and we connect it to a cathode terminal of external source, so that we make this metal object which is to be protected a cathode. And now, we see that electron will flow this way and current will flow this way, and the circuit will be completed like this. The current will flow like this and it will go like this. So, positive to negative terminal, and the current will go out of the auxiliary electrode and enter into the metal, okay, when we have cathodic protection. Now, since this is cathode, okay, so and the current is entering into the metal object. So, that means another concept of another criteria for cathodic protection is we have to see that the metal object, the current should enter into the metal object which is to be protected. So, there are three cases. One is cathode, metal object is to be made cathode. Second is the metal object is to be connected to a cathode terminal of an external DC source. Another criteria for cathodic protection is we should see that the current should enter into the metal object, so that the metal object is protected. So, another is electron should flow into the cathode or the metal, and third is current will enter into the metal. Now, if we come to mixed potential theory, let us get into this board. We will plot potential versus log of current density. Now, there let us take a simple system where both the cathodic and anodic polarization are activation controlled. So, this is my anodic polarization line, this is my cathodic polarization line. Now, if we see that this is the free corrosion potential. Now, if you keep this is metal plus N M. So, actually N plus, this is the anodic side. So, that is what I have written, anodic reaction, metal is going to the metal ion, and this is E reversible potential, okay, if the metal ion concentration is unit activity. So, we can write it as E 0, and this is my I 0, which is the exchange current density at the metal surface, and that is what I have to write M. I 0 of m. And this is another reaction which is I 0 for the cathodic reaction, C for cathodic reaction, and if it is hydrogen evolution reaction, then I 0 should be written as I 0 bracket on m. That means the hydrogen evolution is taking place on the metal surface. Now, this is my free corrosion potential, this is E core and this is my I core. If we keep it like this, so the system will corrode maintaining this current density at a particular temperature and pressure. Now, if we would like to introduce cathodic protection, that means we have to supply electrons to the system, this system if we can supply electron, okay, or if we can introduce negative current or IC, if we increase the IC, this is my IC which is cathodic current density or cathodic current density during the cathodic polarization of particular cathodic reaction, and this is my IA, this is my IC. Now, if we increase IC, what would happen? If we increase IC, the system, the polarization will be enhanced, and the polarization line, the cathodic polarization line will try to take the direction as shown in this figure. Now, let us say I have, this is my corrosion potential. If we measure the potential of this electrode at this condition, we will see this potential is shown. Now, this point onwards we will have extra cathodic polarization because the current value we are supplying cathodic current. So, let us say I have reached to this potential and this is my polarization. This is my polarization, okay, the value of the polarization. Now, at this point my IC is, this is my IC and this is my IA, and IA is nothing but the corrosion rate, because IA is indicating anodic current density. So, my applied current would be this much. This is my I applied, which is nothing but IC minus IA. Since IC is considered to be negative current, so I put a mod value, so that this is the value of I applied. At this value of I applied, I will have this much polarization and this is my current density for the corrosion. Okay. So, this is my new corrosion rate. Actually, my corrosion rate was here, which is I core, which is I core. Now, IA, which is the new one, let us say this is new, N means new. So, this is new. So, IA new is less than I core. So, I have reduced my corrosion, I have reduced the corrosion rate of the metal object in the particular solution. This is the very concept of cathodic protection. Okay. So, I have to somehow take the potential, the corrosion potential, by potential to a lower value compared to the E core value, and I will get rid of, we can reduce the corrosion rate to a great extent. And since this is a log scale, so if we reduce it by, we can reduce it by maybe 2 to 3 order magnitude. Okay. So, we can have a very good corrosion protection. Now, if we keep going along this line, and this is my position of I 0 and ER, okay, and I 0 is nothing but the current density corresponding to the reversible reaction for the forward and backward reaction. Now, if we keep going like this, I keep decreasing the I core, IA, okay, but at the same time we are increasing the I applied. And these I applied will be increasing in with respect to the log scale. So, the I applied would be a very large value if we keep going down. Finally, we can reach to this value, okay. So, which is nothing but the I core would be, IA would be equal to I 0 of metal on metal surface. Fine. That point we can see that the corrosion rate would be minimum for the metal object, okay, and this particular point would be called as the complete protection. Now, beyond complete protection, so complete protection means a very large I applied. So, I have to send a huge current to the system, huge negative current to the system, and that negative current, the amount of negative current would be so large, it could be of the order of 10 to the power 4 to 5 ampere per centimeter square, which is a large current. So, we should not do that, rather we should stop somewhere in between in order to have a realistic corrosion control. Now, what happens if we go down? If we go down, you can go down. If we go down, what would happen? I will see that it is becoming cathodic reaction. This is also cathodic. Okay? So, this part of this metal polarization is a cathodic polarization of metal ion is going to metal elemental metal. So, below this complete protection, instead of having a better corrosion protection, we there could be a situation for amphoteric metal, for aluminum or zinc, like this amphoteric metal, there could be a corrosion again. Okay. The corrosion could be like this: ZnO plus H2O plus 2OH minus, it can go to ZnOH4 minus 2. Okay. So, instead of having protection, zinc ion can go into this complex ion which is dissolving again. So, instead of having corrosion protection, we can have corrosion, and this could be termed as a cathodic corrosion. So, we should not go beyond that. Actually, we should stop in between in order to have a realistic protection at a realistic amount of money which is to be spent. So, corrosion protection by cathodic means is basically taking the polarized potential to a negative side, at the same time sending the negative current and taking the IA value, which is the anodic current density, to a much lower value. Okay. This is the principle of cathodic protection on the basis of mixed potential theory. Mixed potential theory. Now, once we know this, we should see that how many ways we can send negative current to the system. Okay. Now, there are two ways. There are two ways. One is sacrificial anode. One is sacrificial anode. And second one is impressed current cathodic protection. And this is in short we call ICCP. So, let us see first this particular method. In this method, what we do, we have, let us say, a pipeline which is to be protected, and this pipeline is buried pipeline. This is the earth surface, and this is the pipeline. We have to protect this pipeline from corrosion or to control the corrosion rate. What we do, we connect it to another anode material, which could be magnesium or zinc or aluminum. We can connect it to the magnesium electrode or zinc electrode or aluminum electrode, and this is the steel. The material of the pipe is steel. Why we connect it to this magnesium, zinc and aluminum? Because those are highly electronegative compared to steel in the electrochemical series. Fine. Now, once we connect this thing, now this is this is forming a galvanic series. Now this is forming a galvanic cell. Now this becomes anode and this become cathode. So now we have made it cathode in this system, and here we are not supplying any external current. Okay. So the current is coming into the system. Okay. So this is anode. So electron will go this way and current will pass this way. So the concept of having cathodic protection, that electron should go to the material which is to be protected and the current should enter into the system from electrolyte. Okay. So that is what we are having. So this material is cathode and also we are supplying current, we are sending current and the current is entering into the system and the electron is entering into the system through the wire, conducting wire. So this system where we are not using any external current source or power source, and this system is called sacrificial anode. Why? While we have this protection, this magnesium, zinc or aluminum, they will corrode. They will corrode and this steel pipe will be protected. Now this is exactly similar like why we use zinc coating on steel sheet, that means galvanization. We use galvanized steel. There we have a steel plate, on top of that we use zinc coating, and zinc is acting as anode and steel surface will be acting as cathode. And this is a protection which is called sacrificial anode, because the anode material is getting sacrificed and giving protection to the steel pipe. Now in this case, this kind of situation we can have it in protecting water tank, okay, hot water tank, and the system would be like this. The water tank, we can also have a protection. For example, this is my water tank. This is my water tank. I need to protect it using sacrificial anode method. Now this is also steel material and this is, let us say, some water, hot water is kept. Now we can do it like this. We can have a hood which is also made of steel, and from that hood we can hang one magnesium rod. This is magnesium rod. So now once we hang magnesium rod, this magnesium will be acting as anode and this would be cathode. Current will go like this and enter, this is current, enter into the steel tank and the steel tank will be protected. Now when we see that the steel tank is protected because the current is entering from the anode through the electrolyte to the steel object, but at the same time wherever the current is leaving the magnesium rod, that part will be corroded. So here the current is leaving, so this part is corroded. So there is one more point, you please remember this one, that when the current leaves the metal object, okay, so that point is vulnerable for corrosion. Now this is one more situation. Now once we have this knowledge that we can use it for sacrificial anode method, the aluminum, zinc, aluminum, magnesium. So we need to see what are the characteristics of those anode material, because one point is when we are using this, we need to know that what point we can go for this method, okay, or where we should go for this method, okay, how long we can have protection, okay, and then what are the current value that it can supply to the system. Okay, those informations are necessary informations. Okay. So now let us get into those part. One thing is anode material and cathode material, cathode, which is steel pipe, these two, there should be sufficient potential difference between these two. Okay. So, if we have sufficient potential difference between these two, of course, this will be negative, this will be positive, then only we can go for this method. Okay. Second is, it should have a sufficient electrical energy contact. It means, let us say the sufficient electrical energy contact, it means let us say a particular anode material, the rating is given like this. Let us say it's meant as it means ampere hour per kg or per pound. It means that if we send, let us say this is the system, this is my cathode, this is my sacrificial anode SA, this is SA means sacrificial anode. If we supply 1 ampere of current, then 1 kg of anode material, how long it can give protection? How long it can give protection if we send 1 ampere of current to the cathode material. Okay. So, this is nothing, this is called, this is basically the idea of electrical energy contact. Okay. Electrical energy contact hour, I could say contact hour. So, how long it can protect this system if we send 1 ampere current from sacrificial anode to the cathode material. Okay. So, this should be sufficiently high. The another point is, which is very important, that cathodic protection by sacrificial means we should go for wherever we do not have external power source. Some remote places, if we do not have an external power source, then we should go for this sacrificial anode material. No power source, electrical So, there we should go for this sacrificial anode method. Now, what should be the criteria for anode material? Now, we see that the zinc is very good anode material for steel protection. We see that magnesium is a very good protection, very good material for anode in case of sacrificial anode method. Aluminum is also very good, but there are some issues with aluminum. Now, aluminum, there is a tendency for the aluminum to go into passive state. Now, if it goes to passive state, if aluminum, let us say in case of aluminum, if it goes to passive state, then there could be a serious problem. Then instead of acting as cathode, acting as anode, aluminum going to passive, that case instead of acting as anode, it will act as cathode. So, that time if we have a steel with aluminum, this is anode. Now, if we have passive layer on top of this, since this aluminum is a highly passivating metal, so that case instead of anode, this will become cathode, and this becomes, initially it was cathode, later it will become anode, and we all know that the anode material in a galvanic couple corrodes. So, instead of getting protection, this will corrode. So, what should we do? Generally, many a times or most of the cases or all the cases, we have this sacrificial anode. On top of that, we put a blanket, and this blanket, inside that blanket we put some material, that is gypsum. We put gypsum, or coke, bentonite, this kind of material is placed on top of this sacrificial anode, and in case of aluminum we put NaCl. Okay. So, what it does? It is called backfill. This is called backfill. This is called backfill. The function of backfill is, let us say in this side we have steel, iron, now we have connected it. Now, let us say the current is coming like this and entering like this. If we do not have the backfill, there could be a situation the some part of the channel of the soil material is highly conducting. The some part is highly conducting, some part is less conducting with or very high resistance. So, which side the current will flow? Current will take the path of highly conducting path, which is the narrow position. So, that part, and we have seen that wherever the current is coming out from the system of the anode material, that part will be corroded. So, the current is preferentially going through this particular part. Okay. So, we have more corrosion here. Now, it may happen like that this entire part will be corroded and the lower part is detached. So, but the electrical connection or the conducting wire is connected on top of this. So, this part only give the protection, this part is invalid. So, that is why we go for the backfill. What it does? The backfill provide conducting surrounding, uniform conducting surrounding. So, all throughout the surface the current is leaving the anode material, and there would be uniform distribution of current over the entire anode surface, and the anode surface will be corroding uniformly. Okay. That is a very essential criteria for this design of this sacrificial anode system. Now, another part is, if we have this sacrificial anode, it should be used for a shorter duration. Okay. If we go for a very long duration, we have to see that time to time we have to replace this anode material, we have to monitor all those anode material part and all those things. So, generally we should go for a shorter version of protection. Okay. And at the same time the electrolyte should be less corrosive. If it is very highly corrosive, the anode material will be corroded very fast and the protection will be lost. So, this is the part of sacrificial anode method. Okay. Now, there is one more method which is called ICCP, which is called impressed current cathodic protection, which exactly follows this. Okay. Now, here what I do, we have a pipeline, let us say this is the buried pipeline, okay, or some water tank. Let us consider a water tank here, a big water tank which is buried, or some tank material, steel tank which is buried, and this tank is to be protected cathodically. Now, that case we have a rectifier which sends DC current. This is positive terminal, this is negative terminal. We connect this steel material or steel tank to the rectifier, and the negative terminal is connected to this, and the positive terminal is connected to auxiliary anode. Okay. And this is cathode, this is auxiliary anode, since we have connected it to positive terminal, and we send DC current. So, the current is going like this, it is leaving this anode surface and entering into the cathode surface. Now, if this tank is a very large tank, okay, so this part the current is gradually entering. Now, if we consider away from this section where we have this auxiliary anode, we see that the current is traveling a larger distance, fine. And also if we consider this part, the current has to move a further large distance. Now, instead of that, and if the current is flowing like this, the current will move like this path it will take. So, though we can have a protection on this surface, but this surface will not be protected to that extent. Now, we have a technique to avoid to have a uniform protection, but here if you see this rectifier is sending uniform current, constant current to this anode material, and this anode is from the anode material current is coming out and entering into the steel material or the steel tank. Now, here also since the current is entering, this part will be protected. Okay. And here also I am sending negative current IC to this system, fine. Here the cathodic and anodic reaction would be different, because this part is auxiliary anode, and since we are using external power source, the auxiliary anode material should not corrode. It should stay for longer period. That is what we generally use platinum or and nowadays platinized titanium is coming up as a very good auxiliary anode material, which will not corrode and which will act as anode. Its function would be just to supply current to this system. Now, in order to have a complete protection, what we do? We put another auxiliary anode here. AA means auxiliary anode. Auxiliary anode. Now, what we will do? We will connect it to this part, this positive side. Okay. See, if we connect to the positive side, the current is also going to this, through this, and leaving this surface and entering to this surface. So, we have complete protection. Now, when we have this thing, now that time we should be careful that this connection, which is the connecting wire, is basically the wire is conducting wire is connected to the auxiliary anode as well as the cathode material, which is the steel structure. We should have a proper insulation. Proper insulation means there should not be any local cell formation. Let us say this is copper wire and this is steel. So, copper would act as cathode, steel will act as anode in this local zone if we expose this joint to the electrolyte. So, we should have a proper insulation in this portion, so that there should not be any other galvanic couple in the protecting in the steel structure. Now, another point is this current value is to be chosen in such a way that all the time this steel structure is in the solution or the electrolyte, which is basically the soil electrolyte. Okay. That time there could be a various number of reactions that can form on the surface. There could be several local cell formation on the surface, which can be cathodic, which can be anodic. Now, we have to see that whatever anodic reactions are happening, this current should cover up that anodic reactions, so that all the time the current will flow into the system and go out through this electrode, through this connecting rod. This is called impressed current cathodic protection. And here, of course, you see that all the time you have to send current. So, the external power source is required, and this is also little costly, because here you have to also take care of auxiliary anode material, which must have a very good protection against self corrosion in the system, okay, so that it can function for a longer period. And third thing is, of course, here also you see the backfill is kept. Backfill always make the current which is coming out from the system, it makes it uniform distribution of the current. Now, this is ICCP. Now, ICCP has various advantages. Okay. The advantage is basically it can serve a longer protection. Okay. It can make it uniform. It is not dependent on the material, on the corrosion behavior or the corrosion rate of the anode material. In the sacrificial anode case, we need to see what is basically the ampere hour for that particular anode material, but here we should not bother about that, because once we fix the anode material which is not self corroding in the system, and if we can keep on sending this current, we can have a protection. Okay. But it is a little costly method because you need to have external power source. But this can have some other problem which is related to stray current. Stray current related problem there could be possible. How is it is possible? Let us say some company has gone for protection of steel tank, which is buried steel tank. Now, some other company which has laid a oil pipeline just below this entire system. Okay. This is oil pipeline which is laid by another company. Now, this is not protected by this system. What would happen? Now, once it sees that there is another conductor which is passing through this system, the current will also try to move into the system. Okay. So, if current enters into this system, the current has to leave somewhere, and here also the current is entering. Now, this current will leave, and this material, let us say this material is coated, and since it is buried, there could be a possibility that some part would be there will be no coating, okay. Some part would be exposed to the electrolyte. Okay. So, the current will leave from this surface and enter into the system. So, if current leaves this pipeline and enters into the system, this part is protected because current is always entering into the system. But what happens here? Since the current is leaving the system, this part would be corroded. And this is in a highly potential field. So, this will also be polarized, and current will enter into the system, and current will leave from this system to this metal electrode. So, we see that the current is entering into the nearby pipeline, and the pipeline here also current is entering, and it is leaving from the pipeline surface to this system. So, these part are vulnerable for corrosion. Now, if it is painted, so if the some part is exposed because of the wear and tear, erosion, so this metallic surface is exposed only. So, the huge amount of current will pass through this system, and the current density around this region, since this is a very small area and large current, the current density would be huge here. So, gradually there would be a lot of corrosion, and finally, there could be a possibility of leak. Okay. So, this leakage lead to oil loss. Now, this entire thing, basically the corrosion which is happening in the pipeline surrounding nearby pipeline, is because of this stray current. This is basically nothing but the stray current, and this is called stray current corrosion. How to protect this? Because you never know, and you will not be able to know that how long this pipeline will stay and when it will start leaking. Now, the protection would be simply, if we can make this pipeline be the member of, this tank system. So, how you can make the pipeline be the member of this cathode? You just connect this pipeline with the steel tank with the conducting wire, and the surrounding part of the conducting wire should be insulated properly. Now, if we connect it, so current of course will start coming here, because this is in a very highly it is basically a current field. Okay. So, the potential field, so the current will always enter here, here also current will enter. So, if current enters into the system, no problem, we have protection, but when it leaves, that time it goes through the conductor and it goes into the steel tank. So, no case where the current is leaving this system or the pipeline to the electrolyte, that situation we are stopping. And if we can stop this situation, we can protect this pipeline also. Fine. The classic example of this is a pipeline, oil pipeline. There are instances that the pipeline is leaked and there is a huge oil loss because of the stray current, because another company has set one ICCP on top of this pipeline. Another example is in cases in cities where you have tram line, okay, the tram line, below the tram line, if water pipe is going, that water pipe can also come under stray current corrosion, because the tram line, the top part, when it goes, that time it develops a potential field and the current will pass through the current will enter into the water pipeline and it leaves the pipeline and goes to another surrounding metal object. So, there one can also have corrosion due to this stray current effect. And the protection is, you, in case of pipeline, you connect it with the steel tank which is being protected with the help of ICCP. Now, let us see what are the advantage of impressed current cathodic protection. One advantage is it is versatile. It is versatile and it can be applied with a wide variety of situation. Let us say difference in electrolyte conductivity or different electrolyte. Okay. Metal object can be a large object which can be protected. For example, pipeline and this tank both can be under protection because of this ICCP, because the current value is much larger in compared to the sacrificial anode method. Second is, it is also effective in high resistance soil. Okay. Very highly resistant soil. So, the resistance is very large, so the current flow would be less. Okay. There will be resistance to the current flow. There will be, but since we are supplying current from the outside source, we can control the current value and have a protection. Now, third is, let us say I have steel tank and on top of that we have a small coating, let us say paint, non-conducting coating, fine, or if we have, or let us say I have zinc coating, there if we employ this ICCP, the current value which will be needed to protect this would be very small. Now, let us say some part of the coating would be out. If the some part of the coating is out, then the current value will be needed as per the exposed area. So, we can monitor depending on the current what we are sending via this external power source. If we see that the large current is required, that means we will be coming to know that there is a problem with the coating. Okay. So, the coating can be monitored or the coating quality can be monitored. So, these are the advantages. What are the disadvantages? Of course, it requires external power source, and I would not say that is disadvantages, I would say this is a requirement, but it needs since we are having external power source, the cost of having all those systems together would be very large. Okay. So, that is one. There could be a possibility. So, what are the disadvantages? One is high cost. Second is there is a possibility of stay current. Corrosion. Now, so the another point is, let us say when you are supplying large current, now this is cathode, this is anode, you have connected it to positive and negative terminal. So, if you are supplying large IC to this system and if there is hydrogen ion, the hydrogen ion can take this electron and form H2 gas, and it can also have hydrogen atom, and then there could be a possibility of hydrogen related embrittlement effect in the steel. This is another problem. So, these are the advantages and disadvantages of ICCP, and also we have explained about we have also seen sacrificial anode method, and these are the two methods by which we can go for cathodic protection. Now, there is one more protection mechanism which is also falling under electrochemical ways of corrosion protection, that is anodic protection. Now, anodic protection, in case of cathodic protection, we make the steel structure or the structure which is to be protected a cathode, but in this case the structure will remain as anode, but still we can have protection. How it is possible? This is possible in case of active passive metal. Now, coming back to this figure, which is the mixed potential based theory for cathodic protection. Now, let us say, since we are saying that this is anodic protection, that means instead of cathodic polarization, we should go towards the cathodic polarization side. Now, if it is activation controlled and if it is active metal, then if we go towards the positive side, which is nothing but the anodic polarization, we will see that gradually we keep increasing the IA. IA will be increased as we go towards the positive side from this E core point. Now, if we increase IA, that means we are not getting any protection, rather we are increasing the corrosion rate of the metal. Now, if it is instead of active, if it is passive metal or active passive metal, then what would happen? Okay. Now, let us get into that part. We will modify this figure a bit. Now, if this is active passive, let us say, if it is like this, we know that active passive, if we go towards the anodic polarization side, the active passive metal after reaching I critical, it will, the current value, the anodic current density will go towards the left side, and finally it will attain a passive region. This is nothing but the passive region. Fine. And let us say the situation is like this. Okay. And this is my cathodic polarization line, this is my anodic polarization line, and with this we have also seen that if it is mixed potential theory, now the system will go to this point and it will remain there. Now, if by forcefully, if we take the anodic potential or the potential of this metal object or the metal object towards the positive side, further positive side, what you have to do? You have to send extra current. So, that current is decided by difference between IA minus IC. This is my IA, this is my IC, this is IA. So, gradually if we see, if we keep on going like this, we will see that gradually I am increasing my applied current. Fine. Now, if we keep on increasing my applied current, so actually if we will see that the anodic current density is increasing, the anodic current density is following this track. And if we plot the anodic current density with I applied up to this point, let us say this is 1, 2, 3, 4, 5, 6, up to 6. So, I applied and IA, I applied, if we keep on increasing, IA is also increasing like this. So, my corrosion rate will also increase, because IA means the corrosion rate, corrosion of, or the anodic dissolution current for the metal object or metal. Now, we are also going towards positive polarization direction. We are increasing the positive polarization, that means the del E is gradually increasing. Now, somewhat if we can take it to this point, if we take the potential to this point, and that time what would be my I applied? My I applied would be this much. Okay. So, from this, if we jump to this, my I applied would come to this level, this is my starting level, this is my starting level. Now, my I applied would be this much. So, it would be little less, this is my I applied, and what would be my IA there? IA would be like here. So, as we go on increasing the anodic polarization, we are seeing that initially the IA is increasing with increase in I applied, but later once we go to this section, which is the passive zone, my I applied would also go down. At the same time, my IA also will go down. Okay. So, IA will be coming to this. So, I am putting it as a red point, okay, and this is the point we have reached. And if we maintain this potential if we can maintain, what would happen? I will always experience my corrosion rate would be in the passive region. And we have also seen that if we can take it to the passive level, the material corrosion rate would be very, very small. Okay. This is the very concept of anodic protection. Somewhat we have to take the potential to the passive range, and if we take it to the passive range, we will see that there is a very, very small anodic current density, which is equivalent to the corrosion rate of the metal object, and that corrosion rate would be very, very small.